Under supervised machine learning, there's primarily two fundamental functions. So far, we've only considered predictions in the continuous case, which has been all about linear regression. If you have data where the y variable can be represented in a continuous numeric value, it's easy to predict what y is going to be based on the value of x using linear regression. But linear regression doesn't always work. Take the binary example here. X is your typical numerical data, but y is just 0 or 1. There's nothing technically blocking us from running a linear regression, but is it helpful? Not really. Regression is supposed to help us predict the value of y based on x, but this linear regression isn't very predictive in this case. This kind of binary data is very common in a classification task. Based on the number of features or columns of data that represent something, can you model an algorithm that can classify something as 1 or 0? In a real-life example, you may have something like spam email classification based on features like the sender's email address, the content of the text, etc. You classify whether the email is going to go into the spam folder or the regular inbox. Or you may have some image detection algorithm like, based on features of images of MRI scans, can a machine detect when the scanned body part has a tumor or not? Or an algorithm that has learned thousands of pictures of beavers and ducks and can correctly identify an animal as either a duck or beaver. So data that looks like this is commonly used for machine learning stuff, and we need a better shape to describe the trend going on here. This brings us to the logistic function, also known as the sigmoid function. You can immediately visualize that this shape is much better looking than a linear line, but let's break this down a bit. The x-axis doesn't have any requirements. Just like linear regression, it can be any unbounded range between negative infinity to positive infinity. Y values, on the other hand, will always be scaled to the range between 0 and 1. Unlike in a linear regression where the y, like x, was also an absolute number value. In other words, the logistic function scales the y to range of probability between 0 and 1. And since all of the data points are either 0 or 1, the shape of this function becomes this S-shaped curve, where generally the majority of the data is going to be near either 0 or 1, and only a few edge cases will have something in between. Applying this logistic function to the data, you get a logistic regression, which lets you model your data to a probability between 0 and 1. But classification is binary. I don't like to see a value like 0.43, but that does happen. It's like a duck and beaver classification algorithm suddenly seeing this picture of a platypus. It's got features of both a duck and a beaver, so what does it do? In practice, you want to turn the probability into a decision, and you do that with the decision threshold. The decision threshold is typically at 0.5, where if the predicted value is above 0.5, you label it as 1, and if the value is below 0.5, then label it as 0. So no, the algorithm will not be able to create a new platypus category, but if you're looking for that possibility, you'll need another type of model. Binary classification will either put the platypus into a duck or beaver depending on what it thinks it's closer to. You can build this logistic regression to a practical application with a neural network. If you apply the decision boundary to a real data and train it with the neural network will learn to draw the decision boundary in the feature space so that the weighted sum of the points are at the decision boundary. Basically, the neural network will split the 1s and the 0s in a place that makes the most sense. Let's come back to this with a little bit more detail in a minute. But for now, notice how this linear boundary still makes some error. You can easily get an accuracy metric just by calculating the percentage of correct labels over total based on your decision threshold. You can also think about this decision threshold as a linear line in the two-dimensional case, or a plane in the three-dimensional case. Notice that in either cases, we can separate between the two classes with a linear boundary. In fact, even if you have dimensions 4 or higher, which I can't really help you visualize, the decision boundary in the binary case will always be an extension of a line in whatever dimension you go up to. That means even if you have numerous features, which our data usually do, the boundary is still linear. If the linear line can perfectly classify the two classes, we call this linearly separable. This will be an important concept to remember. But before I get there, let's go back to our logistic function, and let's think about the logistic function's loss. First of all, a common question is, can we use the accuracy metric, or 1 minus the accuracy metric, as our loss? Both are measures of error, but the answer is actually no, and there's a mathematical reason that I won't go over. Cut to the chase instead, the loss function will look like this. I'm visualizing this in two cases. The loss when the target value is 0, and the loss when the target value is 1. Again, I won't go over the math, but the intuition is that depending on whether the value is 0 or 1, the loss of the corresponding value gets triggered. So the loss function actually looks like this U-shaped curve. Remember that the value is always between 0 and 1? This means that the loss function will always be shaped like this U curve, and there will always be a global minimum at this point. The gradient descent algorithm can get us to this global minimum, and this can be calculated the exact same way as in the linear regression case. This means that in both linear regression and the logistic regression cases, the machine uses the same algorithm and learns the same way, even if the functions look different. Now, we need to understand how this applies in a neural network. Remember how I said that the logistic regression will always create a linear separation of the data? Well, you might have seen data that look like these. These clearly aren't separable with a linear line. Important fact is that the neural network output is also always a linear combination of the weights and biases, which leads to a linear output. However, if data is not linearly separable, and the linear decision threshold can't reasonably do a good job at classifying, then we need to do something to make this line non-linear. In order to express non-linearity like the logistic regression curve, we have to introduce activation functions. Similar to how we are able to get an S-shaped non-linear regression with the logistic function, we can use an activation function to do something similar to the linear output of the neural network. The sigmoid activation function takes a linear output and maps it to a value between 0 and 1. Through a series of backpropagations and learning over many epochs, this activation function allows the neural network to map the data separated with the linear decision boundary into a curvature, allowing us to effectively classify even in cases where the classes can't be separated by a linear line. This is one of the reasons why neural networks are so effective at understanding the patterns of complex data. The sigmoid activation function is just one of the many activation functions that you can use, and the best one to use will depend on the situation. Some common activation functions include sigmoid, hyperbolic tangent or tanh, and ReLU. Sigmoid is what I just described that'll be used if you want to transform the neural network output into a probability range between 0 and 1, so it's ideal in a binary classification problem. Tanh extends this range into -1 to +1. This makes the gradient much steeper, often making convergence to the minimum quicker than a sigmoid function. Then there's ReLU, which stands for rectified linear unit. ReLU shape is linear only when the value is positive, and when the value is negative, it turns them into 0. It's simple and computationally efficient while also mitigating what's called a vanishing gradient problem, which occurs when gradients become vanishingly small during backpropagation, making learning slow and ineffective. ReLU prevents this from happening by negating any occurrences where the gradient of the function becomes flat. For a multi-class classification problem, there are other differences that you have to keep in mind. In this case, while similar to a sigmoid, the output is more than binary. Each class gets its own probability. With k number of classes to label, we need a normalization that makes all of the outputs sum up to 1. The softmax function does that. Also, the loss function will now most likely be the cross-entropy loss instead of the binary logistic loss. I won't go too much detail on multi-class classification because functionally it's done in a very similar way, just with a different activation function and evaluated with a different loss. Anyway, you now understand another key component of a neural network, the essential idea that non-linearity needs to be introduced to solve a complex problem. Activation functions are a key component of a neural network, and one that you'll most likely include in all of your modeling projects.